Hello everyone. Hello everyone. Good afternoon. And welcome to the day 5 of the student webinar lecture series by the emerging researchers. We are delighted to have all of you here with us as we continue the 6-day lecture series designed to create meaningful learning experiences through student-led sessions and also expert insights from international institutions such as UCCS and UPR. This webinar series brings together emerging researchers, mentors, and then global faculty to explore key academic themes, helping participants build strong conceptual understanding while also gaining exposure to real world applications and evolving research trends. As part of our life science career and research program, this initiative aims to strengthen the academic foundations and expand scientific perspective and connect you with a broader research community. Today's session will be focusing on artificial intelligence, one of the most transformative fields shaping modern science and industry. We'll begin our first theme with the foundations of artificial intelligence and intelligent system, where we explore the core principles of AI, machine learning, and how intelligent systems are designed and developed, which will be followed by the applied artificial intelligence in healthcare, engineering, and scientific research, where we'll look into how AI is being used across disciplines to solve real world problems and drive innovation. Before we begin today's session, it is our privilege to acknowledge and welcome Dr. Sukant Kurana, whose work at the intersection of artificial intelligence, neuroscience, and healthcare continues to inspire students and researchers alike. His vision of building global research ecosystems plays a key role in guiding initiatives like this. So, let's hear a few words from Dr. Sukant Kurana.
Teaching is an important part of growing up as a scientist, to be an impactful researcher, impactful communicator. I wish the youngsters presenting today to a wider audience than just their research colleagues all the best. Go ahead and have a great day. Thank you.
Yes. Now we'll be having our first presenter, who is Hari. He'll be presenting about particularly transformers today.
Good afternoon, everyone. I am Hari Sudarshan, and today we are diving into one of the most important technologies of our time, transformers. These are engines behind ChatGPT, Claude, Gemini, GitHub Copilot, basically every AI tool you have probably used or heard of. By the end of this section, you will understand how they work, why they are such a big deal, and where they are taking us. And even if you have never studied deep learning before, don't worry. This session is designed to explain transformers in a simple and intuitive way. By the end of this webinar, you will understand why transformers were such a major breakthrough, how attention works, and why this architecture became the foundation of modern intelligence. So let's get started. Before we go technical, I believe everyone appeared here would definitely used any of the AI tools. Every single one of those tools run on transformer architecture. Transformers didn't just improve AI, they completely replaced the way machines understand language. They power search engines, image generators, coding assistants, and even medical research tools. Understanding transformers means understanding the foundation of entire modern AI. So, to understand transformers, we have to understand how the revolution happened in this field. So, to understand this revolution, we just need to look into the older models. Before transformers, we mainly used RNNs, which are recurrent neural networks, and some advanced version of RNNs are LSTMs, long short-term memory. Those models processed words one at a time. For example, if we read a sentence like "the cat sat on a mat," in that the model processed like the first, then cat, then sat, and so on. So these caused several problems. First of all, training was so slow because of the computation could not happen in parallel. Secondly, these models struggled to remember information from the earlier parts of long sentence. That issue is called vanishing gradient problem. In simple words, imagine if you are reading a long book but slowly forgetting the beginning of as you continue reading. That was essentially the challenge older AI systems faced. In 2017, a team of researchers at Google published a paper with the title "Attention is All You Need." This paper changed everything. Their core idea was radical in its simplicity. Instead of processing words one by one, what if every word look every other word simultaneously? They called this mechanism as self-attention, and it removed the need of recurrence entirely, which means training could be massively parallelized. You could throw thousands of GPU at the time, and this problem directly gave birth to models like BERT, GPT, uh, and every large language models you know today. So let's dive a bit more deeper. What is attention exactly? Let's use an example, and you can see a sentence in the screen. The animal didn't cross the street because it was too tired. What does the word it refers to? You know it's the animal, not the street. But how? Because you subconsciously paid attention to the right word. Transformers do exactly the same thing. Every word dynamically divides other words in the sentence which are most relevant to understanding its meaning. It learns to attend strongly to animal, and this lets the model understand the context the way humans naturally do. So let's go bit more theoretically. In self-attention, every word creates three things: a query, a key, a value. Query means what am I looking for, and a key means what information do I have, and a value means what should I share. The models compare query against every key in the sentence and generates an attention score, then uses those scores to combine the values into a rich output. The formula on the screen captures mathematically, and here softmax is used to normalization, which will help to make the sum into one, and the square root is used to prevent the score from getting too large. So you don't have to worry about the math if it looks intimidating. The intuition is simply simple. It's like find what's relevant and focus on it, ignore the rest. So a full transformer has two main parts, an encoder and a decoder. Encoder reads and understands the input. It builds a rich representation of what was said. The decoder generates the output. It produces the response, translation, or continuation. Each of these is built from stacked layers of multi-head attention, feed-forward layers, and residual connections that helps gradients flow during training. And also one of the key addition is positional encoding. Since the attention has no built-in sense of word order, we add positional signals so the models uh, knows word one came before word two. So now let's look into what is multiple attention heads and what's attention head. So here is everything gets really interesting. Rather than running attention once, transformers runs multiple attention in parallel. Each run is called an attention head. Each head learns to focus on something different. For example, one head might specialize in grammar, like making sure the subject and verb agree. Another might track semantic roles, who did what to whom. Another might capture long-term dependencies, like connecting a pronoun back to its noun, maybe 100 words earlier. Think of like that. And I will explain with an example. Uh, think like if you are having multiple students read the same sentence and each highlight different things. When you combine all their insights, you get much better understanding than any other single reader. That's the idea of multiple attention heads. So, how does a transformer actually get trained? It happens in two phases. The first one is pre-training. The model is exposed to an enormous corpus of text like books, website, Wikipedia, code base, scientific papers, and it learns to predict next word or fill the missing words. This teaches its grammar facts, reasoning pattern, and world knowledge. Then it comes to fine tuning. The pre-trained model is specialized for a specific task, like being a chatbot or translating language or writing code. The key insight here is scale. The bigger the model is, more data, the more compute, the better and more surprising capabilities will become. So pre-training at scale gives us large language models, LLMs. Look at the chart. This is the parameter count for models produced by Google. In 2018, BERT started with 340 million parameters. In 2019, it became GPT-2 it with 1.5 billion parameters. And in 2020, GPT-3 jumped into 175 million parameter. And the today's model are estimated in trillions. With this scale, the capabilities are nobody fully predicted. The ability to have conversations, summarize documents, write and debug code, reason through multi-step problems, and generate creative content, and so on. Researchers call this emergent intelligence, and the abilities that appear almost spontaneously as you scale up. So here is something people often miss. Transformers are not just for the text. Attention mechanism is so powerful that researchers have applied in almost every domain. For example, in computer vision, vision transformers treat image patches like words and achieve state-of-art results. In audio, the models like Whisper use transformers for speech recognition, and in science, AlphaFold is used transformer-based architecture to solve problems. And today, multimodal models like Gemini Ultra or GPT-4V can reason across text, image, audio, video simultaneously. So transformers have become the universal architecture of modern AI. Now, let's be honest, transformers are not perfect. Training a GPT-3 cost estimated around 4 to 5 million in compute, and it consumed an enormous amount of energy. Models can hallucinate confidently, state things that are completely false because they are pattern matching machines, not knowledge databases. They can produce and amplify the bias present in their training data, and they do not truly reason in the way humans do. They are extraordinarily good at pattern matching, but that's completely different from genuine understanding. And also, there are real concerns around misinformation, deep fakes, job displacement, and privacy. These are the challenges the field is actively working to solve. So, where are we headed? Let's look into the future of transformers, a few exciting directions. A, first of all, s- smaller and more efficient models. Researchers are finding ways to get GPT-4 level performance at a fraction of compute cost. Second, longer memory. Early model had tiny context windows, but today we are at millions of tokens, and this is expanding fast. And third, AI agents, systems that don't just answer questions, but it autonomously plan, take actions, use tools, and complete complex multi-steps. The and the big one everyone is debating is AGI. Will scaling transformers will eventually lead to AGI, the artificial general intelligence. Companies like OpenAI, Google DeepMind, and Anthropic are actively racing towards more capable, more general AI systems. So the next decade will be fascinating. Let's bring it all together. Transformers are replaced slow sequential processing with parallel self-attention. That was a fundamental shift. Self-attention lets every word to relate with every other word, capturing context at any distance. Multi-head attention extract multiple types of relationships simultaneously. Scale more parameters, more data, more compute. Unlock the capabilities of nobody predicted. And transformers are now power to not just language, but also in vision, audio, science, multimodal AI, and all. So if you remember one thing from today, that's attention changed everything. Thank you so much for your time today, and I would love to hear your thoughts.
Thank you, Hari Sudarshan, for such a detailed explanation on the past, present, and the future path of AI. Now, I'll be explaining a similar thing in terms of the foundations of AI. I'm currently working as an AI engineer and a startup right now. So, the foundations of AI. Here, one thing that we can start with is a similar explanation that Hari Sudarshan had given, that it is based on transformer. Transformer is the most particularly forefront of the AI right now. It is the basic architecture which is being used across all any AI agents and AI solutions that you see in enterprises and all that. So what happens behind that particular transformer is the input embeddings and then the output of it. But we have seen how transformers and even how AI is being used to generate songs and posters and even write code, particularly at the moment, right? And the most newest thing that we have seen is the Claude Opus 4.7, and even about how the cyber security of it was in the forefront of the news recently. So what happens when you give a prompt to generate a song, to design a poster, and to write a code? We'll see how that works in the background of it. And then before that, let's see what is inside AI. So what is an AI? AI is something that is mimics human intelligence, including the handwritten rules. It might be similar to how we had automation previously, and that has with some of added intelligence, it becomes AI. And then machine learning is a model which learns patterns from data. It might be the recommendation systems that you're using on Netflix and even the recommendation products that you get on all the e-commerce sites. It might be Amazon, Flipkart, and all that. And deep learning comes in terms of the facial recognition systems that we have in our systems or in our phones and in the fingerprints and all of that. And LLMs, when we come to LLMs, the basic of LLM is the transformer. So next, let's go ahead and discuss what happens, the three pieces of math behind every model. We know that in terms of mathematics, there are like functions that are being used to calculate, but what does it actually do? So we have three sections of it, which is linear algebra, probability, and calculus, each used for a different case. In terms of linear algebra, we use vectors and matrices, where we turn words, images, and sounds into numbers a computer can work with. That is what in the previous lecture you might have seen the explanation of it, how it gets converted based on the probability of what might be the next word. That is what linear algebra does. And then in terms of likelihood and uncertainty, it decides what comes next after going through that. And then the calculus of it improves the model itself by figuring out which way to nudge its parameters. Let's say you give a prompt and then the answer that you got is not something that you're expecting, then you nudge it back with an even detailed prompt, right? And that nudges the model or the agent to work in a direction similar to what you're expecting by changing the weights of it. So we can see here in terms of a simple explanation of a sentence where we have like king, queen, apple, and orange. Here the big idea is each word becomes a long list of numbers, a vectors. Like the example you can see on the screen here. It becomes a long list of numbers, and the numbers with similar meaning get similar numbers. So that king and queen here you can see that they sit together because they have similar numbers. So when an AI or when you're training an LLM, when you train it on multiple levels of text or bunch of text, millions of tokens that are being trained it on, what happens is it groups the numbers together or words together in a similar vector. So all the words which in that similar area gets similar numbers, and then they are grouped together so that it knows already what to expect when this is given, and the relationship between those words are built accordingly with that. Here, that's how the prediction works in terms of when we add probability to it, because here you can see in the cat sat on the, here it might be the cat sat on the bench. Based on that, the training words, whatever you train it on, and based on that, it predicts the very next word. It makes a guess, and then it measures how wrong it is, and then adjusts that thing, and then repeats the same thing until the error goes down to the lowest, to closest to zeros and ones. So all the errors and everything will be measured in 0 to 1s here, and then it keeps on fixing its weights until the loss is at the negligible level, where then it can confidently give the answer based on the question that the user is asking. So your sunset over mountains, it can be a prompt. Then what happens is that gets broken down into pieces, and then those pieces become embeddings, which is the vectors that I've shown earlier, where it becomes a set of numbers. And then based on that, probability comes in where it predicts the very next word. And then based on that, random pixels are generated. When we talk about image generation, what happens is this text can get converted to random pixels, which are also converted to values. So those pixel values get arranged randomly, and then based on the input given by the user, those values keep on altering the basically pixels to generate an image that the user is describing for. That's how image generation works, similar to how text generation also works. Here we have seen similar patterns in Claude, in Gemini, in Suno, and even in Claude Copilot, where the input is a text prompt and the output is basically a text reply. In Gemini, we get text prompt to image, and in Suno, in terms of audio, we get like lyrics plus style into audio track. It generates a whole song based on it. And with Claude Code, we get code plus question. We get codes based on the, it can get the access to the entire repository, where it reads your repository and gives you codes based on that. So it comes down to where the word becomes numbers and embeddings, and generation is repeated probability. Models learn by measuring their mistakes. That is the basics of it. But how does this apply in real world in terms of across disciplines and all that? Let's see that next in a moment. Now next I'll be speaking about how this particular basics and foundations are part of. Yes. So here you can see that inside the engine of an LLM, we have transformers, we have AI agents of the present, and even all the research directions that are going in the direction of agentic AI. And we have the multimodal models. What happens is, in the previous lecture, in the previous video, we saw that the transformers work in a way where they are like encoders and decoders, where the encoding value takes in and then decodes the value and then gives you the output. In the same way, when we apply it to a real world scenario, the transformers work in a way where they are like encoders and decoders, where the encoding value takes in and then decodes the value and then gives you the output. In the same way, when we apply it to a real world scenario, the transformers work in a way where they are like encoders and decoders, where the encoding value takes in and then decodes the value and then gives you the output. In the same way, when we apply it This is how I'd mentioned images get broken down to. It gets broken down to a vector, and then once that becomes a list of vectors, the same transformation works where it matches that, and then based on the error and comparing it to the user input, it keeps on fixing it until the final output is generated. It is very similar to how even poster generation, song generation, all of it works is very similar to how text things works. But only thing is it maps more values rather than comparatively compared to only the text generation. So we have an agent. Right now, LMs work in a single way where it takes the input and gives you the output based on the data it has been trained on. But how does agent come in where it performs actions for you? It might be any simple agents, right? It can be like a job searching agent. It can be something that replies to mails. It can be a personal assistant, which is one of the forefront of things being built now in any startups or anything. You see personal assistants which can send mails, which can set up meetings and invite others also in terms of that and record meetings and do all of those things personal instances. That's what agents are being used to do nowadays. And what does agents like even the Claude Code do? Like how is it built on basically? It is think, act, and observe and repeat until the task is done. You might have given used any prompts to in Gemini or even Claude if you have used it or any other AI tool. When you give a prompt, what happens is it thinks and decides the next step based on the data it has been trained on, and based on that it gives an output. And if the output is not meeting the benchmark set to it, then it repeats the cycle again until that benchmark is crossed and it gives a valid output based on the evaluation frameworks used in that particular agent. So what happens when one agent isn't enough? You can think of it like a researcher writing a research paper, any thesis it might be. So even that it can be used with a multi-agent system where each agent we can give a job, one supervisor, one researcher, one writer, and one reviewer. It can be someone, a supervisor guides the researcher to find the information and research based on that, and the writer writes that particular research and the outputs of it found in that. And the reviewer reviews it before finally giving the final thesis paper of it. So across sciences, it is being used in different fields. We have AlphaFold, which predicts like protein 3D structures in chemistry, in physics, in climate, in agriculture, and in medicine. AI is being used across all the industries right now, where they are trying to replicate the offline workflows to be done with the help of artificial intelligence to save up time and to stop burning money businesses. That's how they are being built and being worked around right now. And today's takeaway is that transformers and attentions, the model learns from earlier pieces matter before predicting the next one. And agents, they just don't answer, they think and they act. And same architecture in every science, it is being used across based on the use cases. And then we are getting solutions. And even the research way, we are heading in a way with AI where it is overtaking all of the work which was previously being done in like days. It is being done in minutes at the moment. So that's how AI is transforming the world of technology, science, and pretty much in every other industry it is being entered into. And with that, I conclude my lecture. And next we'll be inviting Shubh to explain on his lecture with imaging. So Shubh is currently pursuing Bachelor's of Engineering in Thapar Institute of Engineering in Patiala, Punjab, and he'll be speaking today about medical imaging. And yes, over to Shubh.
Is my screen visible, Prajwal?
Yes, yeah, it's visible.
Okay. Okay. So, good afternoon, everyone. My name is Shukar. As Prajwal introduced, I'm a final year undergrad studying at Thapar Institute of Engineering Technology. Today, I'm speaking on the topic like a theme which is applied AI in healthcare engineering and scientific research. So, the session before mine, in which the Prajwal covered about the foundation of AI and how these systems learn and develop. And now I'm talking about so they're talking about the applied AI in medical imaging from pixels to diagnostics. And I want to promise upfront that that this is not going to be a list of impressive results. This is going to be an honest talk about how AI can and AI like AI can do medical imaging and what it cannot do yet, and why the gap between these two things matter enormously. So let me walk through. What we'll cover today, so you'll know where we're headed to. So we'll start with some context why medical imaging specifically, and why it's the hardest domain for AI, and then we'll cover the core technical blocks, the CNNs, the transformer, the segmentation, detection blocks, and then we'll talk about the key domain by domain about ophthalmology, radiology, neurology, pathology, and see what AI can do and what AI is actually doing in every particular area. Then cover the part that I think is the most important and the most underappreciated, the deployment challenges. What goes wrong when you take a model that performs beautifully in a lab or in a certain setting, and then you put into a real hospital. And then we'll talk about the distribution shift, the federated learning, the fairness, and the interpretability. And finally, then we'll look ahead about at foundation models and what responsible deployment actually looks like. Okay, so I just want to ask everybody over here, so why medical imaging? Why is the domain that I've chosen to focus on? So as we know, it's the scale of the problem. Like firstly, there are like 3.6 billion medical imaging procedures performed every year gradually and globally. So X-rays, CT scans, MRIs, ultrasound, fundus photographs, histopathology slides, and the volume is staggering. And about the 75% and about the 70% of all clinical decisions that are directly informed by the imaging data. That means when a doctor decides whether you have a tumor, whether your retina is healthy, whether the lung shows signs of infection in the majority of the cases, and image is involved in that decision, or basically image is the driving factor. And here the number of the trained radiologist and the imaging specialist is not as growing as the same rate of volume of imaging data in many parts of the world, including the large parts of India. There are simply not enough specialists. Rural households, rural hospitals, community clinics, they don't have access to the same expertise as the major urban centers should be. And this is exactly where AI enters the picture, not to replace the clinicians. I want to be very clear about that, but to augment them. So to help catch what might be missed at 2 a.m. when a radiologist has reviewed their 100 scan to enable screening programs in places that previously had no access. But what is the key phrase I want you to hold on to the entire lecture is the medical imaging data is highly dimensional, annotation scarce, and highly sensitive to population and equipment variation. That sentence contains the core challenge of this entire field. Everything we'll discuss today flows from it. So moving on, let's ground this direct comparison. What does the traditional analysis look like, and what does the AI change? Traditionally, medical image analysis requires a trained expert, a radiologist, a ophthalmologist, or a pathologist to manually examine each image. That takes time. So depending on the complexity, it takes hours. It's also inherently subjective. Two radiologists looking at the same chest X-ray can reach different conclusions. That's called inter-data variability, and it's a documented, well-studied problem in medicine. So AI flips several properties. A trained model can process an image in milliseconds. Its output is reproducible. The same image will always produce the same prediction. It can be deployed on mobile hardware, enabling screening in lower resource settings. So, and critically, it's the detect subtle patterns, things that are technically present in the image but fall below the threshold of human perception under normal working conditions. Now, I'm not presenting that AI is like super superior to clinicians. The table on this slide is not a celebration; it's a representation or it's a description of complementary capabilities. The radiologist has contextual understanding, clinical history, and the ability to ask why the patient follow-up questions and those decades of judgment. So the AI has speed, consistency, and the pattern detection at scale. The goal is to combine them and to bring the best of both the worlds, basically. So the as in the CNN, the workhorse. So let's talk about technology, and we start where almost all the medical imaging AI starts. That is a CNN. The core idea behind the CNN is very, very elegant. Rather than hand engineering features, I'm telling the algorithm, look the particular edges, look for the particular texture, look for the particular features, etc. So on and so forth. A CNN learns those features directly from the data. You show it thousands of label image, and it figures out layer by layer what patterns to predict and what outcomes to give. Okay, the architecture has a recognizable flow that you can use on this slide. A raw image in convolution network, extract features, pooling, normalization, and compress and regularize dense layers, make the final prediction output comes out. In the medical context, output might be a disease classification, a severity score, or a probability map. The key innovation has that made medicine was a transfer learning. We don't always have 100,000 labeled images. Annotation requires expert time and is very expensive. But we can take CNN pre-trained on image and millions of natural images and fine tune it on the particular data set of medical data set of even 1,000 of images, and the low level features, edges, texture, shapes, etc., so on and so forth, transfer remarkably well. And then there is a GradCam, a gradient weighted class activation map. This is how we make CNN decision interpretable. GradCam produces a heat map over the input image showing which regions most influence the model's prediction. In clinical setting, this is not optional. A clinician needs to understand why the model flags something before they act on it. A black box that says the patient has a cancer is not clearly deployable. A system that says a patient has a cancer and this is the region which drove the prediction is a tool which a clinician can engage with basically. Okay, so CNNs dominate a field of nearly a decade basically, but around 2020, so VITs, that is vision transformers, enter the picture and change the things significantly. So the key differences are very architectural. The CNNs process the image locally. A convolution network, a kind of filter, looks at a smaller neighborhood of pixels at a time. Transformers treat the image as a sequence of patches, compute attention across the entire image simultaneously. This means that a transformer can model relationships between different parts of the image and the relationship between a lesion in one corner and the tissue pattern in other in a way that particular scene fundamentally cannot. In medical imaging, the global context of which is very clinically meaningful. The appearance of one region of a scan can only be interpreted correctly in the context of what the surrounds it. So we also have a specialized transformer variants such as SegFormer for segmentation tasks, Dino for self-supervised learning, SAM for segment anything model from Meta, which is currently being actively adapted for radiology users. So now segmentation deserves a particular attention because it is fundamentally different from classification. Classification says this image contains a tumor. Segmentation itself says this tumor occupies exactly these pixels. That distinction matters enormously clinically. Tumor boundary delineation is required for surgical planning and radiology targeting. So UNET, with its encoder-decoder architecture, skip connections, has been a dominant segmentation architecture in medicine for years and remains very highly competitive. As an illustration example, in one of the multi-model studies that I have conducted, a dual stem vision transformer to disaster imagery, the architecture has 88% severity classification, accuracy, and 51.9 MIU, that is mean intersection over union score. I'm demonstrating that the transformer-based architecture generalized effectively to any high-stakes visual domain, not just radiology. So let's now talk specific domains, and I want to start with an ophthalmology eye imaging because it's one of the earliest and the most successful areas in medical AI deployment, and it illustrates both the promise and the nuance of this field beautifully. The eye is a very unique feature of ours. It is the only organ of the human body where the vascular rate and the blood vessels can be directly observed non-invasively. You don't need surgery, you don't need a contrast agent. You point a fundus camera at the eye and you can see retinal blood vessels directly, and that's because the blood vessels are connected to the systemic circulation, and eye can reveal signals of diseases far beyond vision disorder, diabetes, hypertension, and even early neurological chances basically. Sorry. Let's go through the major application. Diabetic retinopathy. So one of the leading cause of the blindness globally is characterized by microanems and hemorrhages in the retinal vascul sorry vascul vasculature. So a Google DeepMind published a landmark paper in 2016 showing that the system matched accuracy of retinal specialist. That was a turning point for the entire field. So next is the glaucoma detection. So this involves estimating cup to disc ratio from the fundus images. A key metric automating this removes a significant bottleneck in glaucoma screening programs. Next is age-related macular degeneration. OCT imaging allows cross-sectional views of the retinal layer Hello. Hello.
Yes, yeah, sure. Yeah, you're audible. Yeah.
Okay. Okay. Actually, I got cut in between, I guess. If I'm not. Is my screen
Yes, yeah.
visible?
Yes, yeah, it's visible. Yeah.
Okay. Sorry. Okay, so chest X-ray is one of the single most common imaging study performed globally, and the CNN-based systems for pneumonia detection have been shown to match the exceed radiologist level performance. During the COVID-19 pandemic, AI triage tools were deployed at scale in hospitals across the multiple countries. So, which help and prioritize which patient needs urgent escalation in overwhelmed emergency department. That was a real world deployment under genuine crisis conditions, not a controlled trial. So, lung model detection from a CT is another compelling use case. A CT scan of the chest might contain hundreds of cross-sectional slides. A radiologist reviewing all of them for sub 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 centimeter nodules, tiny potential carrier, early stage lung cancers under time pressure is exactly the kind of risk where AI augmentation provides a measurable value. 3D CNN that produce the volumetric data that directly have shown a strong performance here. On the neurological side, the brain tumor classification from MRI is one of the most studied examples in medical imaging. CNN transformer hybrid architecture that shows the combined local as well as the global features reach above the accuracy of 95% to distinguish the glioma, meningioma, and pituitary tumors. So importantly, these results have been achieved with the architecture specific design to efficient under clinical compute constraint, not just a large cloud scale models basically. Now moving on to the Alzheimer detection is particularly exciting because AI can detect subtle hippocampal atrophy patterns in MRI years before clinical symptoms manifest. That windows of pre symptomatic detection is potentially where intervention was the greatest impact. And stroke early detection from the diffusion weighted MRI directly guides the treatment urgency decision. The speed of AI inference, like not in even seconds, but it's like milliseconds, matters the accurately how when the brain tissue is dying. So moving on to the next, which is the let me cover the most important next frontiers of the medical imaging, which are computational pathology and the multimodal fusion. So histopathology slides, the glass of slides in which coming together and forming up to a digitize of 1 lakh cross 1 lakh pixels. So in which we which is called the whole slide image, which can't be processed directly using a CNN in one pass. So the dominant approach is styled patch analysis. Divide the slide into very smaller patches, analyze each patch, and then aggregate into patch level prediction into a slide level conclusion. The elegant algorithmic framework for this is multi-instance learning, which is MIL, which allows slide level labels like the slide contains cancer to supervise a model without requiring pixel level annotation. The pixel level annotation on pathology slide would require a pathologist to manually outline every tumor cell, prohibitively expensive. So MIL sidestep this problem. Moving on to current applications, including the grading prostate breast and maybe the cancers from H&E slide detecting a mitotic features, a marker of tumor aggressiveness and quantifying tumor infiltrating lymphocytes, which are increasingly important as biomarkers for immunotherapy responses. Now, moving on to multimodal responses fusion. So, the future of clinical AI is not single modality; it's a multimodal. So, because everything we know, for example, a person will not be a clinician or a pathologist will not be able to tell the particular has particular disease from seeing a particular image. So it has to see the report, the genetic marker, the clinical notes, etc., and so forth, and each of these information so can be analyzed to one of the very famous model, which is CLIP. A CLIP style contrastive learning has enabled joint image text embedding spaces. You cannot only train a model on pair etiology images and their corresponding reports, and the results understands the both modalities jointly. As a practical illustration, as I've done, a thalassemia iron overload stratification system that fuse multi-modal clinical features with imaging data achieved a sub-second inference on ARM class devices. That's not a cloud deployment. That's a system that can run in rural screening camp on a device that costs a few $100s. That kind of accessibility engineering, in my view, is important as the model accuracy itself. Okay, so now we arrive at the core problem, which is the distribution shift now, because everything has been so impressive with the benchmarks and the values, but now we are here at the specialist matching performance, all of it's a contingent assumptions which violating the real world. So the assumption of the data is you deploy on the looks like the data you trained on, but it's not, and it's never, it almost never does basically. So now we are coming to problem with distribution shift. So let me give you concrete forms where it takes and how it takes. So first is the scanner variability. So for example, different MRI scans, different companies, different brands. For example, a model was trained on 3 Tesla scanner, and the data that is being tested is a 1.5 Tesla scanner. So that's from different institutions. The pathologies are different basically, and basically the scanner variability is different. Second, the population shift. For example, if the data is being trained on the Western population and is being tested on Indian population, so the model would not be implied to the geography that it is being across to, and then there will be a population shift. Second is the label noise. So third is label noise. Basically, medical annotations are not objective grounded. They reflect annotating clinicians training, their institution diagnostic criteria, their specialty conventions. Two different annotations produce different labels for same image. For example, the model learns from those labels and inherit the subjectivity. Okay, then moving on to the temporal drift. So disease pattern change, treatment protocols evolve, patient population shifts, and a model trained on 2019 pre-COVID check rates have learned features for that no longer characterize the current population and the current patient population. So the sentence that I want at the bottom of the slide is one of the most important to remember. The benchmark accuracy is not a deployment reliability. A model that achieves a 95% accuracy on held out tests from the same institution that generated the training set tells you almost nothing on how will it perform on the deployed elsewhere. This distinction is the central challenge of the stream. Okay, moving on to distribution shift problem. It's not obvious to collect more diverse data from different institutions. Why don't we just do that? Because medical data come with a privacy concern. It has like privacy legal protections measures from HIPAA in US and GDPR in Europe, and equal framework in different jurisdictions in India, and so on and so forth. So federated learning is the principal FL, that means federated learning is the principal technical solution to the constraint. The core idea is elegant. Instead of moving the data to the model, you move the model to the data basically. So look at the diagram of the slide. So how it is like hospital A, B, C, and C keeps patient data entirely local. A shared global model sent to each institution. Each institution trains it locally on their own data and computes the gradient updates. So only those gradient updates, not the raw data, are sent to a raw central aggregation server. The server combines the gradients using the algorithms like fed average or fed prox, and then sends an updated model back and reiterates. So what happens is federated learning introduces its own challenges. The most significant is a non-IID problem, that is non-independent, non-identical distributed data. Each hospital has a different patient population, different disease prevalence, different imaging equipment. Averaging gradient from heterogeneous distribution can actually hurt the performance. You end up a model that performs adequately everywhere but excellency nowhere. So personalized, and the second with the personalized FL, so clinical specific FLs averaging the rare condition. For what does that mean is, so so selective aggregation, only sharing the gradients for relevant parameters reduces communication overhead while preserving the performance on rare or institution specific conditions. Second is the minority, and then moving on is a third minority class F1 score is a particular revealing metric in this context. If a federated model improves the minority class recall, it means that the collaboration is genuinely helping with rare condition that no single institution has enough data to learn from alone. Okay, so distribution shift has a specific and particularly serious manifestation in clinical AI and algorithmic bias, and I want to spend a few minutes on this. Like, it's just not technical problem; it's an ethical one. So it's a demographic bias. So when training data is not representative, if a majority of your training images come from patients of a particular ethnicity, then the model will perform worse on the underrepresented group. This isn't a theoretical problem it's a documented problem. So, for example, a study in 2019 has been conducted so that dermatology AI performs significantly worse on the darker skin tones because training dataset were predominantly light skinned. So in clinical deployment, that means the patient who already face the greatest barriers to healthcare access are also once most likely misclassified by the AI tool. Okay, next is the label and the screening bias runs deeper. So what be the diagnostic instruments we use, a questionnaire, the clinical criteria may themselves encode historical bias. If a screening instrument for a mental health condition was developed and validated predominantly on one demographic, its scores may systematically misrepresent another demographic. AI trained on labels from another inherits the bias. Next, bias up from pre-training. So imagine was curated from diversity. Medical imaging models that use image and weights inherit its demographic and photographic biases. This needs to be actively audited, not assumed away. On the interpretability side, GradCam gives a saliency map that shows which image and which regions which drive the prediction. SHAP values decompose the prediction into feature contribute calibration. Testing tells us whether the model confidence scores are trustworthy or not. So as an anecdote I want to present here is a clinical NLP pipeline using birth topic to detect a gender bias in eating disorder screening instruments. It's a direct example of AI being used to audit AI. The finding that the standard screening tools produce differential performance across gender groups has directly implications for how those tools are used clinically. That kind of audit is not optional. It's a prerequisite for responsible deployment. Next is evaluating the AI model accuracy. So first is AUROC score, which tells us about the starting point for the binary classification. It measures how the positive and negative class has been separated. Second is the sensitivity and specificity encodes the clinical trade-off. Sensitivity is how many true cases does the model catch, is a miss rate. Specificity is how many negatives does the model correctly rule out, is a false alarm rate. So calibration is underappreciated and critical. For example, so this is a very important thing. A model that outputs 90% confidence should be right 90% of the time. If it's only right 60% of the time, at 90% confidence, the model is overconfident. And in clinical settings, overconfident wrong predictions are dangerous. ECE, which is expected calibration error, measure this systematically. Subgroup analysis is non-negotiable. You must report the performance broken down by age, sex, ethnicity, scanner type, institution. Silent features where aggregate performance looks fine, but a specific subgroup performs badly are the most dangerous kinds of failure in clinical AI. So a small method is I will share here is clinical studies of language model probing using imbalance evaluation set creates a what are called saturation artifacts. So the model appears well calibrated simply because the dataset is very skewed. So the balance evaluation recovers the true signal. The point generalizes. The evaluation protocol is itself a variable. Its design choices can make a biased model appear reliable. Next is the foundational model. So the field is now we're undergoing a significant paradigm shift from task-specific models from scratch for each clinical application to a large foundational model where we can train a vast corpora and adapt it to clinical tasks with minimal label data. So MedPalm is a Google medical language model, and GPT-4 is with vision capabilities have both demonstrated near specialist level performance on clinical multiple choice benchmarks. Moving on to SAM is a Meta's SAM model, which is general purpose segmentation model that has a zero-shot transfer on medical structures. You provide a prompt, a click, a bounding box, and a segment and structure. This prospect of interactive clinical segmentation based on SAM is generally exciting. Next, moving on to BioWill Check Zero is a clip-style contrastive pre-training radiology reports and image pairs. The resulting models can perform zero-shot chest X-ray diagnosis, classifying whether they were never explicitly trained to classify because they have learned the joint semantics of radiological language and visual appearance. Moving on to next, which is knowledge grounded alignment, a coupling language model. So reasoning with structured medical diagnostics. So represents an attempt to make model very verifiable against external conditions rather than simply making the proxy task performance. Okay, let's now address what responsible AI means. Clinical in the loop is a foundation principle because AI in medicine should augment clinical judgment, not replace it. Moving on to the regulatory compliances in India, clinical AI systems are regulated by CDSQI software as a medical device. In US is FDA as a 510K pathway, and so on and so forth for every country. Prospective monitoring models secret silently after deployment. Patient population shift, equipment get upgraded, new disease variants emerge. Continuous performance monitoring and statistical drift detection as our operation requirement, not optional additions. Equity by design. So diverse training cohorts, mandatory demographic stratification in validation, and community engaged data collection are not nice to have. They are minimum required to avoid systematic disadvantaging already vulnerable population. Transparency. Institutions that deploy AI must disclose their training data sources, validation cohorts, known failure mode, and performance on subgroups. This is a beginning to be codified in regulation, but the ethical obligation exists regardless. And finally, the edge and the rules of deployment, quantization, model pruning, and efficient inference pipelines are what make clinical accessible in the setting that need it most. A system that only works in a well-resourced urban hospital with a GPU cluster is not a solution to a global health inequity. It's a solution for people who already has global access to the care. Moving on to the last that was so first I would like to make key takeaways from this lecture, which is the first, the medical imaging is rich, highly dimensional, and annotation scarce. That combination makes it both ideal test bed for AI and hardest proving ground. Don't let impressive benchmark numbers offset the difficulty of underlying problem. Second, CNN and VITs are not magic. They learn statistical correlation and training data. The question that undermines the real world value is whether those correlation hold the deployment environment. Always ask this particular question is what is the training distribution and what does it match where this it should be used. Second is the distribution shift is a central challenge, not architectural choice, not data set size, not understanding when your model assumption hold and failing gracefully when they don't. And it's a core engineering skill of the clinical AI. Interpretability and fairness are the prerequisites, not afterthoughts. Any system that affects patient outcome must be auditable, calibrated, and validated across the demographic group. There is no shortcut here. Large foundation models are promising, but unproven at scale is in clinical deployment, sorry. So external validation on diverse real-world cohorts remain the gold standard. Be skeptical of the benchmark performance. Be rigorous about the real-world evaluation. Thank you so much.
Thank you, Shub, for such a detailed explanation. You also, spoke about the limitations of deployment and scale when it happens. Even though many of the research things pass through in the research stage, when it comes to actual deployment, many of the agents, even currently, that is one of the biggest challenges in enterprises and anywhere in the world. Proving to be able to scale that it works at a scale is the challenge that we are facing with. And thank you for pointing that out too. Next, we have Sohit Reddy, who is currently pursuing Bachelor of Engineering in Bioinformatics to speak about AlphaFold, which is one of the areas in which AI is being applied at the moment. So let's welcome Sohit.
Hi everyone, this is Sohit. I'm excited to be a part of this Day 5 student lecture series again. This is Sohit, and today I'm going to present on applied AI in healthcare, in specific AlphaFold in today's lecture. So we'll talk about how this specific AI tool has changed structural biology and also medical research. So first I'll explain what problem it solved and why it mattered scientifically, and how researchers use this specific GitHub repo and the database, and where its limits are. And if you're new to this structural biology, think of this talk as a guided story from protein sequence to the medical impact. So in this lecture, the main agenda is that we'll understand why a specific protein structure matters and what AlphaFold is and why it transformed and how it transformed our current healthcare research. And we'll talk about the workflows, and we'll talk about its limits, and also we'll have a quick 1 minute careers and takeaways at the end. So before AI, we already knew that the structure is pretty much central to the biology, protein structure. A protein sequence is like, a sentence written in amino acids, but the biological meaning emerges when that specific sequence falls into a three-dimensional structure. It could be a beta sheet, it could be a helical structure, or it could be a loop. So that shape tells us where a drug could go and bind, and why a specific mutation in that chain causes diseases, and how or why a pathogenic protein interacts with the host cell. So the ability to predict that structure is not, just a technical convenience, but it changes the questions we can ask, because the structure basically needs targets of the protein could affect the folding, because disease causing mutations could destabilize certain domains of that protein, and it could alter the interfaces and also shift the conformation state, which could cause the disease. And predicting that structure is pretty much expensive through manual methods like X-ray, NMR, or cryo-EM. These are absolute powerful tools, but it could take months to years to just get one structure. For example, me, while I was in Japan at KEK, which is High Energy Research Accelerator Organization, where I was interning last year around the same time. So I was working with X-ray crystallography. So it was like a painful process for me coming from a bioinformatics background, because I always was doing dry lab, working on my computers, not knowing what's actually behind the scenes, behind the data. But then when I actually entered, like when you're trying to crystallize the protein, it's pretty much easy. But when you're trying to loop it out and put it in some other medium, or like shifting between the medium when you're trying to crystallize it, uh, you have like a mocktail of solution. You need to take that crystal into there. So it's kind of really painful process, because these crystals are so delicate. Like it takes a lot of patience, a lot of expertise in order to take out that crystal and put back in. So I broke like 10 to 12 crystals in my first go. So it was a real painful experience for me. But I also tried cryo-EM at KEK at Structural Biology Research Center, second building. So there I was working with cryo-EM, and it was pretty much easy there. But again, we were working with copper plates, and put back in the liquid nitrogen medium and push back in, and it goes into the machine, and then you take that sample and you expose that to a certain machine, and then you get those into a system, and then it basically looks like a black and white image, and from that black and white image they make a protein structure. Can you imagine, like a pure black and white image, from pure black and white image where you can't see anything, and they build a protein structure out of it from those copper grids. So yeah, so if you have a chance, you can just YouTube and see some of the videos, like how the work is actually done there, how X-ray crystallography works and how cryo-EM works. So I did crystallization, and then we could take those crystals, store that in the liquid nitrogen cylinder, carry to the synchrotron, and you could submit the sample to the synchrotron manager, and he could give you access to the server, and you could remotely access that how do you, if there is a crystal, and now it is so automated that you can modify that rotator or whatever that machine is which is injecting x-rays on the crystal. You can modify and you can choose which part of the crystal to target, and then you get lot of files, and from those files you build a structure. So I was actually asking my supervisor, why not we just take a crystallized protein and we do all this stuff for my entire 2 months? But it is not possible in just 2 months. It takes a lot of time. But we already took a known protein they have already done for a specific protein. I took that for a crystal and I read to that, and they gave me some sort of files, XYZ map files and more other files. I imported that into Moran software. I was trying to fix bonds, water molecules. It was a lot of chemistry, stereochemistry, which I was very weak at. And I was trying to solve the protein structure on my own there, and of course with the help of the supervisor. So it was a real painful, a real experience there. And also cryo-EM was also a long process, because the making part is easy, but the analysis part is so tough. So that's why it could take months to years to just get one structure by one researcher. So this is where the AlphaFold becomes not just like random GitHub up repo or something like that. It's not only a science story. The research paper has really mattered in this case, because the public code release mattered almost as much, because it lets labs adopt the method directly, because once the code was open, the field could reproduce, adapt, benchmark, and integrate into pipelines in their own labs, and benchmark and integrate into pipelines of their structural biology or drug discovery. In practice, this turned a major breakthrough into a shared infrastructure. And now on their GitHub you can see like 141k plus stars, 2.5k plus forks, and also the open source release in 2021 by for AlphaFold 2. Now we have AlphaFold 3 currently by Google DeepMind. So when I look at such forks and stars, I keep thinking of my GitHub repo because I barely have two forks for my GitHub repo where I integrated two different workflows from two different labs in one single workflow, which really helped my lab and my work. But yeah, so if anyone wants to explore, you can just go to sohitpydev, SOHRTHPYDEV. It is my GitHub ID. You can go there and explore my profile. Look at fork so that it gives me a boost. Yeah, someone is currently using my work and I'm doing something. So yeah, so now I'd like to present AlphaFold as a sequence of tipping points. First came a competitive success in CASP 13. So AlphaFold places first and shows deep learning can significantly improve structure prediction. And then comes to 2020 with CASP 14 where the organizers recognize AlphaFold as a solution to the 50-year-old problem where the protein folding problem with median error below 1 angstrom and about 3 times better accuracy than the best system. And then they published a Nature publication along with the code with detailed methodology. And AlphaFold 2 is currently open source. And we have like 200 million plus structures that expands to over 300 million in the upcoming year. And AlphaFold 3 and AlphaFold server extend predictions towards molecular interactions. So the reason AlphaFold felt revolutionary is not just accuracy behind it, but also because of the speed, because it just computes in minutes, because uh, DeepMind states that structures that once took years and major budgets can often be predicted in minutes using AlphaFold. And now 200 million plus proteins are actually there with 3 million plus global users from like 190 countries. So the key shift in our current research culture, as far as I can see, is that instead of asking, can we ever get a structure for this target, many labs have started asking if this particular model, if it is AlphaFold or any other model, is it confident? How confident is that, and what experiment should be coming next? So that is the current shift in the research culture. So for students who want the computational picture, this is the operational flow. So you usually begin with a sequence, typically the FASTA sequence, so one or more chains, and then you build the evolutionary evidence, and then you generate the candidate structures, and then you inspect the confidence rather than blindly trusting one model. You generate multiple models and get that confidence value, which is usually measured through PTM and PLDVT, so which I'll come in the next slide. So README is also a good reminder that their GitHub README page is also a good reminder that transformative AI can still be computational heavy. In real labs, compute infrastructure and workflow engineering still matters a lot because most of this work is intensively GPU heavy. So you need access to a GPU system. It could be through your own university or lab server or a shared HPC which I use, or your own local system which has GPU in it. So those are the possible avenues. And also you can use Colab Fold, which is on Google Colab, which you can use where you can use GPUs for a limited amount of time where you can practice stuff. So now we'll talk about the use cases, and drug discovery is one of the easiest places that AlphaFold penetrates in. So that is where AlphaFold holds value. So imagine you're working on a protein target with little or no structural data. So instead of waiting for the full experimental data to get from the lab, you can actually start doing something with the AI generated structure. So you can ask questions, you can ask smarter questions earlier. So the important phrase here is a starting point because docking and medicinal chemistry still requires validation, right? So if you get that structure, do the docking, do the simulation, you could still go forward with the help of AlphaFold structure. But that is not entirely the case because I'm currently a research assistant at the Changang University, Taiwan. So I understand because we currently use BART food model of APCC complex which causes cancer. So we have the lab structure from some Japanese lab. I don't remember the name exactly. We currently use this structure for our docking and simulations purposes. And there is also an AlphaFold model. So when you compare these two, there are no way similar because the sites which we are targeting, the amino acids, the target sites which we are encountering, which we are trying to inhibit, those kind of sequences completely opposite in alpha model. So these are some sort of limitations where you tend not to use the alpha model, but instead use the real lab model. In some cases, you need to be using AI model instead of that. In some cases, to perform simulations. So for every model you choose, you need to back up with a scientific reasoning, I would say. So here is where AlphaFold help because it provides structural hypothesis for protein lacking solved experimental structures, and it also supports pocket inspection, residue level reasoning, target assessment, and also it feeds simulation data, docking data, and various other stuff, and also it improves prioritization before expensive wet lab campaigns. So it is a massive breakthrough in this space. So why it matters in industry and also academia. So when a disease target has no experimental structures, so people usually rely on homology models. So homology model is basically a template based design. So AlphaFold often gives a much stronger starting point rather than the homology model, especially for hypothesis generation and early stage screening. But this does not mean that this is the like the final druggable state. But it can shorten the the path to the testable model. And the second use case over here is the rare disease and variant interpretation. So here you can see you can map mutation sites. So variants can be located on active sites, hydrophobic cores, and also disordered segments or interfaces. And from then, researchers can ask whether a substitution for that specific part likely disrupts stability, folding, or binding to generate hypothesis. And then you support it with a function experiments, like those predictions can actually guide you to make your own rescue assays, mutagenesis studies, or domain focus studies. So important caution here is that while using AlphaFold is that it could explain why a variant might matter, but by itself does not prove pathogenicity. So clinical interpretation still depends on laboratory validation. It could involve phenotyping, it could involve genomics, it could involve population frequency studies or segregation studies. And the third use case is protein complexes and interactions because most biology is not about, isolated proteins floating here and there all by itself. So proteins actually go and form complexes. That is their nature. They interact with nucleic acids, they interact with other proteins, and they switch partners depending on the context. So that is why moving from single protein folding to an interaction mode modeling is such a big deal in healthcare because many diseases often occur through protein-protein interactions and protein-protein complexes. So, and not just from one specific isolated state in most phases. So, if you talk about the AlphaFold multimer and AlphaFold redirection, so their GitHub has this thing called alpha 3 corrective, which emphasizes interactions among proteins and other biomolecules, and this is pretty much important for signaling pathways, enzymes, antibodies, and host pathogen biology. And the medical relevance is that you can understand the interfaces disrupted by disease mutations. You can prioritize residues for interface mutagenesis studies, and the model assemblies that drive signaling or aggregation, and you can also frame new ideas for therapeutic inhibition or stabilization using such studies. So one of the best teaching points here is that AlphaFold gives you a model and an uncertainty language, which I talked before about the confidence. So good users do not just open a PDF file and celebrate, right? They look at the confidence scores, which comes through PLDT, PAE, and also PTM. So PLDT is per residue confidence from 0 to 100, PTM is overall confidence in domain packing, and PAE is predicted aligned error, which is pretty much useful for relative positioning confidence. So how do you interpret? So you need to trust high confidence regions more than the flexible loops, the high confidence regions, and you need to treat the low confidence regions as something. It could be insufficient information, or it could indicate flexibility, or it could indicate disorder. So you never know. So you need to validate that, and you need to inspect interfaces and domain arrangement before using the model for design. All right. And when a technology reaches hundreds of millions of structures and millions of users, it basically becomes an infrastructure, right? So that is a useful word for students to remember. So AlphaFold is no longer just a clever model. It is part of the everyday workflow in many labs. So at the same time, the widespread use does not remove the need for careful validation. So as I said, 190 countries, 200 million plus structures, and 30% plus share of alcohol citing papers are related to disease according to DeepMind. And what this matrix implies that there is a very high global democratization of structure access, just because there are many under-resourced labs where they cannot perform XRC or NMR or cryo-EM to get the structure, so it democratizes the structure access. And the second is the disease research relevance has become so high recently, and dependence on downstream validation is still essential from these metrics. And there are certain limitations the students and everyone in this lecture should remember is that the predictor structure is not the same as the dynamic behavior in the cell. So you need to make sure the protein is mimicking in the cell. So for that you need to use morphodynamic simulations, or you can use AI synthetic cells in order to find out how a protein is actually working in the system. So you need to perform that simulation, and also in vitro, in vivo, and all that stuff. And also some flexible, disordered, or multi-state systems remain very much difficult. So this is also one sort of scientific limit here. And also the binding pockets issue between inactive and active conformations. And also if there is any missing loop or factor, cofactor, the predictions could be a little weaker. So you need to uh, do some sort of analysis over there in order to come up with a good prediction. So, and also here, their GitHub repository explicitly says that their output is not approved for clinical use and it's not a substitute for medical advice or diagnosis. So, because basically, if you want to give a clinical decision, you need to have regulatory, experimental, laboratory, patient level evidence, right? So, if you don't have that, you cannot claim it. So, responsible communication is as important as much as you have the technical skill out there. So the skill pipeline for students is that if you're interested in computational, first learn Linux, Python, containers, and how to optimize GPUs performance, and how to use HPC, and how to make reproducible pipelines. That's how you get started. If you're interested in biological aspect, you start with assays, you start with protein chemistry understanding, you start understanding structural biology like I did while my stay at KUK. But most of my stuff is still in computation. I just wanted to explore the science behind the protein structure prediction and stuff like that. So that's why I did my internship there. So from that I got to know that yeah, that's really important. You need to understand the disease mechanisms if you're really interested in biology aspect. But something that is both useful for biology aspirants and computational aspirants is that analytical thinking, because you need to have confidence interpretation, because whenever you get the model you get the confidence, and from that confidence you need to interpret how confident you are with the model's confidence, and how do you benchmark, and how do you criticize the docking values, and how do you understand the model limitations according to your system. All right. So the good capstone project examples could be like the one I did during my molecular modeling course during my undergrad, is that you could take a disease relevant protein and inspect its PLDT and PAE values, and you can compare with any known structures, and you can analyze the mutation hotspots, make some heat maps, and understand which residue is doing what, and propose one experiment or docking workflow in order to validate your biological hypothesis. So this is one of the best capstone project if you want to pursue one. So these questions are designed to move the class from, you're just listening passively, right? So from passive listening to scientific judgment. So I would encourage you guys to answer them by your own if you can. So if AlphaFold structures predict one confidence structure, does that mean the protein has only one biologically relevant confirmation? So this is something you can Google up, use AI for help. And in a drug discovery project, what experiments would you run in order to trust your docking results from an AlphaFold model and not the lab model? So how do you trust that result? And how should researchers communicate the AI generated evidence? For example, you took model from the AlphaFold, you did docking, you did simulation. How do you communicate that evidence to clinicians? How do you explain that? How do you explain that to wet lab scientists? So what skills should a modern biomedical curriculum should add because of tools like uh, AlphaFold? All right, so these are some things which could be discussed among yourself or by yourself on your own. And we'll move on to the ethics part. We have done the ethics part. Now we'll talk about the key take-home message. So if I had to reduce the whole lecture into one sentence, it would be this. So AlphaFold has changed the starting line of biomedical research. It made structure available at an unprecedented scale, which accelerates discovery, not just structural protein discovery, but also drug discovery. But the destination still requires careful lab validation, whether it is through experiments or your logical interpretation or your responsible judgment. So that balance between enthusiasm and rigor is the important lesson that I want you guys to remember. And I hope you got the key take home messages from my own learnings from my time at Japan, from my time in Taiwan, and I hope you like this lecture. And if you have any questions, you can email me at sohith.dme@gmail.com. sohith.dme@gmail.com. Thank you so much. Have a great day. Bye bye.
Yes, thank you, sir, for a detailed explanation on the AlphaFold and the applications of AI within it. Now we have Hari Sudarshan again, who will be explaining about NLP. Hari Sudarshan has a background in robotics and AI from University of Glasgow, and now he'll be speaking about NLP and the agents, AI agents, basically.
Good afternoon, everyone. My name is Hari Sudarshan, and I am a recent MSc graduate from the University of Glasgow in robotics and AI. So, in our last session, we went deep into transformers and we covered how attention mechanism works and how self-attention replaced sequential processing and how scaling transformer models gave rise to LLM we use today. This presentation builds directly that foundation. Now that we understand how transformers are work and how they perform their actions, and naturally, the next question is what can we build from there? Today, I'm going to answer that by walking through a real engineering project, an AI-powered financial research agent. This is a system that takes a transformer architecture we studied and put it into work in one of the most data-intensive domain there is, which are financial markets. So let's go into that. Before we dive into project itself, I want to set a stage for why NLP matters right now. NLP is no longer a niche research topic. It's becoming fundamental foundation for infrastructure across virtually every industry. In healthcare, NLP is being used to summarize clinical notes or assistant diagnostic and so on. In education, there are so many personalized AI tutors. In cybersecurity, we can detect the phishing patterns and extract the threat intelligence from unstructured feeds. And in legal cases, It's we can analyze the contracts at scale, and the common thread across all of this is the ability to process and understand unstructured text, and that's exactly what modern NLP excels at. Large language models are now being embedded to core workflows rather than just being used as a standalone tools. Understanding NLP is understanding where AI goes. So, why did I choose finance as the domains for this project? Finance is one of the most text-heavy domains in existence. Every day, thousands of news articles, earnings report, SEC filing, analyst report, and economic releases are published, and every one of them contains signals that could affect investment decisions. The challenge is that no human analyst can read all of it in a real time. There is simply too much. On top of that, markets move very fast. A sentiment shift in a news cycle can have immediate price impact. NLP is uniquely positioned to address this, and it can extract insights automatically and detect sentiments and emerging trends, summarize lengthy reports in seconds, and surface relevant signals for analysts to act on. So, and also, finance isn't just a good use case, it's one of the most compelling ones. So, let me be more specific about the problem I set out to solve. So, financial analysts and researchers today spend a significant portion of their time doing the things like autom uh, things which are frankly automatable. They are manually searching across multiple data sources, reading through lengthy reports, looking in for data points, or comparing opinions from different analysts, tracking sentiment shift in news, and then manually synthesizing all of that into investment insights. The process is slow, inconsistent, and doesn't scale. So our goal is of this project was to build an AI agent that could do that heavy listing automatically, retrieve the right information, analyze the sentiment, answer natural language queries, and generate concise research summaries so that analysts can focus on higher order judgment and decision making rather than uh, information gathering. So, what exactly is the system? At its core, it's an intelligent research assistant that sits at the intersection of several powerful technologies. You have a large language model, in this case, Llama 3 or GPT, provide the reasoning and generation capabilities. You have a RAG pipeline, retrieval augmented generation, that grounds the model's output in real retrieved documents rather than purely relying on parametric memory. You have a financial NLP layer for domain specific tasks like sentiment scoring, and you have tool-based agentic reasoning, which allows the systems to plan, search, retrieve, and synthesize across multiple steps. The result is a conversational system capable of answering financial questions, summarizing reports, analyzing the market sentiments, and doing all of this from multiple sources simultaneously. So let me walk through the high-level architecture. When a user submits a query, for example, what is the current market sentiment for Apple? That query first goes through a processing layer where it's cleaned, embedded, and prepared for the retrieval. It then hits the vector database where semantically similar financial documents, news articles, fillings, reports are retrieved using embedding-based similarity search. Those retrieved documents are passed as context into LLM reasoning layer, which generates a coherent and grounded response. The key components powering these are an LLM like Llama 3 or GPT-4, or vector database like Pinecone or ChromaDB, and sentence transformer models for generating embeddings, financial data APIs as the data source, and fastest API or Flask for backend serving layer. So let's go one level deeper into NLP techniques that power this system. At the text processing level, Raw financial text is tokenized, cleaned, and converted into dense embedding that capture semantic meaning. For the core model backbone, we use transformer architectures like BERT and Roberta for classification and understanding of tasks. Llama 3 as the generative backbone, and then RAG pipeline is the central to the system's accuracy. Instead of asking LLM to answer purely from its training data, which could be hallucinated, we retrieve fresh, relevant documents at query time and inject them as context. Finally, sentiment analysis module classifies the tone of financial news and analyst commentary, generating signals that an agent can reason about when forming research summaries. This brings to me what makes this system agentic rather than a standard language model. A traditional LLM responds to a single prompt and stops. It has no memory, no tools, and no ability to take follow-up actions. An agentic system is fundamentally different. It can plan a sequence of steps to complete a task. It can call tools, search engines, and APIs or calculators or whatever during the task. It can retrieve information, evaluate what it found, and decide whether to search again. It contains context across full workflow to make sure this is concrete. If you ask the agent, like, summarize Tesla's recent earning sentiments, it doesn't just generate text from the memory. It searches financial news sources, retrieve most relevant documents, and extract key data points and run sentiment analysis and then generate a grounded summary. That's the full pipeline, what makes genuinely useful for a professional research context. Moving a system like this from Jupyter Notebook to production, which requires a robust engineering stack. On the ML side, Python is the deep learning foundation. Hugging Face provides pre-trained transformer models and fine-tuning infra, and LangChain handles the LLM orchestration and agent calling logic. And the backend is built on Fast API, which gives us clean and high-performance REST API, and containerized the application with Docker for consistent deployment. And for the data infra, we can use vector databases, and for the vector similarity search, financial data APIs like Alpha Vantage or Yahoo Finance for financial market data. On the deployment side, the system is designed for cloud deployments, AWS, GCP, Azure with Kubernetes for orchestration, and CI/CD pipelines for automated testing and release. Each layer was chosen significantly and specifically for its performance characteristics in its kind of retrieval heavy and latency sensitive application. So I want to be honest about the challenges because they are real and they are important. The most significant is hallucination. LLMs can do generate plausible soundings, but act factually that's incorrect in financial information. In a domain like this, where bad informations can lead to bad decisions, that's a serious risk. So precisely why RAG is so important. Grounding the model in retrieved documents significantly reduce hallucination rates. Real-time data reliability is another challenge. Financial APIs can be unreliable sometimes or delayed, or sometimes it might be incomplete. Then domain-specific terminology is harder than it looks. For example, ticker symbols, regulatory acronyms, or financial jargons, and so on. And those require purpose-built training data or fine-tuning. Also, context retrieval accuracy, making sure the right documents are retrieved is non-trivial and requires careful chunking and re-ranking strategies. Latency is another concern, and in a fast-moving market environment, we have to really concerned about the latency, and finally the explainability. In a regulated financial environment, you can't just say AI said like that or AI said so. You must need to show the reasoning. These aren't unsolvable problems, but they require careful engineering decisions. Looking ahead, I see five key directions shaping where the technology is going. First, multi-agent systems. Rather than a single generalist agent, you have had a network of systems connecting across multiple domains. This allows agents to collaborate across financial security, full research pipeline with minimal human checkpoint. Then, perhaps most importantly, institutional adoption and explainable AI systems that don't just generate output, it shows their reasoning in a way that satisfies compliance and regulatory requirements. And fourth, real-time market event processing. Agents that detects breaking news and generate instant research brief within a second of market moving event. Fifth, personalized AI analyst. Systems that adopt to an individual's investment thesis or risk tolerance or portfolio composition. The pace of progress is significant, and I think we are only at the beginning. To summarize what we have covered today, NLP is transforming industries at scale. Finance is one of the most impactful domains given how dependent it is on unstructured text. The combination of LLMs and RAG is what makes it possible to build research systems that are both powerful and grounded in the real data rather than a hallucination. Agentic architectures take this further by enabling multi-step tool using workflow that can genuinely automate complex research tasks. And building systems like this responsibly requires thinking carefully about engineering quality, domain expertise, and the limitations of the technology. Not just what we can do, but also where it can fail. I hope this gave you a clear view of both the opportunity and challenges. I'm happy to take any questions and thank you very much for your time.
Thank you, Hari, for your beautiful explanation regarding the implementation, architecture, and the challenges, and also the way the future of AI is in terms of enterprises with the help of Fusion Agent, finance agent that you explained at the moment. And you explained even about the RAG architecture, which is the most used architecture at the moment across industries to be able to keep the information returned by the LLMs to be grounded to the source of the information. So next we have covered AI in medicine, AI in enterprises. Now we'll be moving to AI in geology. Next we have Shruti with a background in MSc geology who will be explaining about AI in REE, which is rare earth elements, and she'll be explaining about AI demand and AI recycling within the REE. Over to Shruti.
Myself Shruti. Today I am going to present a topic on the AI demand versus rare earth supply chains, a strategic bottleneck. This presentation focuses on how the rapid growth of artificial intelligence is increasing global dependence on rare earth elements and critical mineral supply chains. Although AI is usually discussed as software and algorithms, in reality, AI depends heavily on physical infrastructure such as semiconductors, GPUs, data centers, cooling systems, elements that possess unique magnetic, thermal, optical, and electrical properties. Even though they are called rare, many of them are relatively abundant in Earth's crust. However, economically valuable deposits are limited and geographically concentrated. These elements are extremely important in modern technologies. For example, in digital transformation, they support semiconductors, displays, and data storage systems. In clean energy, they are used in electric vehicles and wind turbines. And in national defense, they are critical for radar system and missile guidance and advanced military electronics. This makes rare earth elements strategically important for both economic and technological development. Different rare earth elements have different industrial applications. So, neodymium is one of the most important because it is used to manufacture powerful permanent magnets used to EV motors, hard drives, and wind turbines. And dysprosium improves magnet performance under high temperatures, especially in electric vehicles and advanced motors. Cerium is widely used in glass polishing and catalysts and optical systems. Lanthanum is important for batteries, camera lenses, and petroleum refining. These materials form the physical foundation of many advanced technologies, including AI infrastructure. This slide shows the rapid expansion of AI infrastructure worldwide. The AI industry is growing at an extremely fast pace, with the market projected to exceed $1.8 trillion by 2030. Training advanced AI models require enormous computational power and energy consumption. For example, GPU shipments increase dramatically between 2020 and 2040. Data center investments reach hundreds of billions of dollars, and AI workloads continue to double rapidly. This growth directly increases the demand for rare earth elements because of AI systems require large scale hardware infrastructure. Many AI related technologies depend heavily on rare earth elements like GPU and semiconductor required specialized materials for nanoscale electronic manufacturing. Electronic vehicles use neodymium and dysprosium magnets in traction motors. AI driven robotics rely on precision motors, so servo systems containing rare earth magnets. Wind turbines use large quantities of neodymium based magnets for efficient electricity generation. Even modern defense technologies such as guided missiles and radar systems depend on the rare earth compounds. So, the rare earth elements are deeply integrated into modern technological systems. The rare earth supply chain consists of several stages like mining, refining, processing, and manufacturing. Each stage creates economic, environmental, and geopolitical changes. Although multiple countries produce rare earth ores, but China dominates the most critical stages, especially refining and processing. This creates a highly concentrated supply chain. If disruptions occur in one region, the impact spreads globally across industries such as AI, semiconductors, renewable energy, and defense. This slide highlights the concentration of global rare earth production. China controls the majority of global rare earth mining and an even large share of refining capacity. This dominance gives China significant strategic influence over global technological industries. Countries such as United States, Japan, Australia, and India are now investing heavily in supply chain diversification to reduce dependence on Chinese processing infrastructure. This has become both economic issue and the national security concern. One of the biggest concerns today is the strategic bottleneck created by the concentrated supply chains. China's export restrictions on minerals such as gallium and germanium demonstrated how mineral resources can become geopolitical tools. Many countries still lack independent refining infrastructure. Trade conflicts, sanctions, and export control can disrupt semiconductor manufacturing and AI development worldwide. As AI becomes more important economically and militarily, rare earth will likely intensify further. Although rare earth elements are essential for advanced technologies, their extraction creates serious environmental challenges. Mining operations generate toxic waste, radioactive minerals, water contamination, and deforestation. For example, the Boato mining region in China is heavily affected by industrial pollution ornamental and and improve extraction efficiency. Another major solution is rare earth recycling and urban mining for electronic waste. Countries are also attempting to diversify supply chains. Long-term sustainability will require like cleaning mining technologies and better recycling systems, international cooperation, and responsible resource management. Without stable mineral supply chains, further AI growth may face serious limitations. In the ending, one thing like rare earth elements are the physical backbone of modern AI infrastructure. And so, thank you for giving me this opportunity.
Yes, thank you, Shruti. Thank you for speaking about the impact of AI on the rare earth elements and how it is dependent on the rare earth element for scaling. And before we close, and I just want to summarize something which we have discussed so far in this webinar. And yeah, before that, we'll be covering one more presentation from Shruti about the AI-driven discovery, recycling, and the future of rare earth materials. We in the previous lecture it was discussed about the impact of AI and the demand of it. The next presentation.
Myself Shruti. Today I am going to present about the AI driven discovery, recycling and the future of rare earth materials. This presentation focuses on how artificial intelligence is helping solve one of the biggest modern technological changes, the sustainable management of rare earth materials. Rare earth elements are essential for advanced technologies such as hardware, semiconductors, electric vehicles, and wind turbines and defense systems. At the same time, mining these materials creates a serious environmental and geopolitical problems. So, this presentation discusses how AI can help to improve material discovery, recycling technologies, and sustainable resource management. Rare earth elements are a group of 17 metallic elements, including the lanthanides and along with the scandium and yttrium. Even though these elements are not truly rare in terms of abundance, concentrated and economically extractable deposits are limited. These mean these materials are extremely important because they possess unique magnetic, thermal, and electrical properties. They are used in advanced electronics, lasers, magnets, and clean energy systems and defense technologies. One major issue is that the global supply chain is highly concentrated, especially under Chinese control. Another issue is those minerals are difficult to replace because alternative minerals usually provide lower performance. This slide shows how deeply rare earth elements are integrated into modern technologies. In electronic vehicles, neodymium magnets are used in motors while dysprosium improves heat resistance. Wind turbines depend on permanent magnet generators, and the smartphones and semiconductors are rare in displays, vibration systems, and miniaturized electronic components. Even AI data centers and high performance computing systems depend on rare earths based on hardware components. So, rare earth materials are not limited to one industry, they support the entire modern technological ecosystem. The demand for rare earth elements is increasing very rapidly because of digitalization and clean energy transition. Industries such as AI, electric vehicles, renewable energy, and semiconductor manufacturing are all competing of the same resources. However, supply chains remain highly concentrated geographically. This creates a fragile global system because disruptions in one country can affect industries worldwide. Another major problem is that mining and refining rare earth elements are environmentally expensive and technologically complex. Although rare earth elements are important for green technologies, their extraction creates major environmental problems. Mining operations produce large amount of toxic wastewater and chemical wastage. Heavy metals and radioactive minerals can contaminate groundwater and surrounding ecosystems. The extraction and refining process also consume large amount of energy, contributing to greenhouse gas and emissions. So there is a contradiction. We need we need rare earth for sustainable technologies, but obtaining them can damage the environment if not managed properly. This is where artificial intelligence becomes important. Traditionally, discovering new materials could take many years or even decades. AI can now accelerate this process significantly. Machine learning model analyze huge scientific data sets and predict uh, promising material combinations before physical experiments are conducted. Digital twins stimulate mineral behavior under uh, real world conditions. Robotic laboratories can perform automated experiments much faster than traditional research work methods. Large language models can even analyze millions of scientific papers to identify hidden research patterns. So, AI is transforming the way materials science reach is conducted. AI is also improving rare earth recycling technologies. Computer vision systems can identify valuable components from electronic waste with a very high accuracy. Robotic systems can automatically dismantle devices such as batteries, hard drives, and motors. And advanced sensors combined with the AI algorithms can rapidly identify environmental composition. Automated recovery systems help to maximize recycling efficiency while reducing chemical use and energy consumption. This is important because recycling may reduce future dependence on new mining operations. The idea of a circular economy means continuously recovering and reusing materials instead of depending only on new extraction. Rare earth recycling can significantly reduce environmental damage. For example, recovering rare earths from electronic waste saves large amount of raw ore extraction and reduce toxic emissions. A successful circular economy would create lower mining pressure, lower pollution, and more sustainable supply chains. This is becoming increasingly important as global demand countries to raise. This slide highlights some real world example like cyclic materials in Canada uses AI associated recovery methods for extracting rare earths from EV motors and wind turbines. Google DeepMind developed GNOME, which discovers millions of potential crystal structures using AI. Redwood Materials in the United States uses machine learning to improve battery recycling process. Research institutions such as KTH Royal Institute in Sweden are also using AI to optimize bioleaching techniques for rare earth extraction. These examples show that AI is already being applied in practical industrial and research settings. Thus, this slide discusses further possibilities. Between 2025 and 2030, AI-driven recycling and urban mining are expected to become commercially valuable. Between 2030 and 2040, autonomous recycling systems and bioleaching technologies may become more common. By 2050, further technologies may significantly reduce independence on the virgin mining through advanced recycling and AI designed materials. So the future of rare earth management will likely depend on the combination of artificial intelligence, robotics, and sustainable chemistry and international cooperation. In conclusion, I would say the future success of AI technologies will depend on not only on the software innovation but also how responsibly we manage critical mineral resources. So thank you for giving me this opportunity.
With that, I would like to conclude by saying AI is something which is rapidly growing in across industries at the moment. Today you might have learned about transformers and the basic architecture of it, and also we learned about the applications of it across industries from medicine to financial industry, and then even for the research of RE. So, for all the speakers, thank you for your presentations today, and for everyone who has joined, thank you for joining of the day 5 of the student lecture series. Hoping to connect with you soon, and we'll be seeing you in the next one. Thank you.